Hello.
Good morning, sir.
Morning. Can you hear me?
Yes, sir.
Yes, sir.
My screen
Yes.
is visible to you.
Yes, sir.
Okay.
Yes, sir.
And you got the notes now? Check your email.
Yes, sir. Got it.
So all of you check your email. अपना email check करिए. Numerical differentiation and integration. Please
Yes, sir.
open the slide number 10. You can also see it from here. And in case you want to refer the previous slide or next slide, then you may open your this notes also. Okay. So in last class we did this topic of finite this using finite difference. We calculated the first derivative of the function. Now in a similar manner we can make calculations for the higher order derivatives. So here we are going to have a look how to calculate the second derivative of any function using this finite difference approach. So based on first derivative, the Taylor series expansion can be used to derive the numerical estimate of higher derivative. To do this, we write the forward Taylor series expansion. So I have written this forward Taylor series expansion at a step size of 2, that is 2 I plus 2. So from equation number 12, you can see that step size is 2h. This is the same Taylor series which we were using. And again, we can write it as expressed in terms of taking in step size of unity, step size of 1. So what in order to get the equation number 14, we can multiply it by 2 and subtract it from equation number 12, and which results in an equation for the second order derivative using forward forward differentiation. Okay, and this is you can see all the terms are in I plus 1 and I plus 2 from equation number 15. So I move to next slide. So in a similar manner, we can calculate for this backward finite divided difference and write the equation in this expressed as equation number 16. And for the central difference method, just we saw in our previous class, we can compute it very easily, taking the three interval I plus 1, I and I minus 1. So equation 17 may be rearranged in the form given by equation 18. It is you can see that it is a combination of forward difference method and backward difference method, and additionally we have divided with the interval h. So you can see here that just as the second derivative is derivative of a derivative, second divide difference approximation is difference of first two divided difference. Okay, so using this approach, can we calculate this second derivative, that is using the center difference approximation, that is using equation number 17? Can we calculate the second order derivative for the given function at x is equal to 2 and using two different step size, first with 0.25 and second with 0.125? Let us see who can give the exact answer first. Any one of you?
Sir, exact 288.
Okay, Ayush. So Ayush, you give the calculator this using the center difference method.
Sir, exact value I am saying.
Okay. No, I know that you are saying exact value, but in the question we have been asked to estimate this using this center difference approximation. That is using this equation number 17. Equation number 17, we are supposed to give the answer using equation number 17. You have the slides with you. You can go back to previous slide. Look at the formula. That is xi plus 1. What is be I plus 1? Who can tell me I plus 1 when h is equal to 0.25?
2.25.
2.25. That is I plus 1. Okay. You calculate the value at x is equal to 2.25, and what will be I minus 1? Xi minus 1. Somebody else from except Ayush? Riyanshu? Ashish?
So 1.75.
1.75. You compute the values, and you can you know the exact solution. You can calculate the percentage error with respect to that true exact answer or true value. You can express in terms of percentage, or simply you can express it in terms of difference. Abhijit, you got the answer? Abhijit. Okay, so you work out on Abhijit. Amrit? Ankit Sarkar? Avinash Roy? Avnish Roy, sorry. Ayan Mukherjee? Bablu Kumar Patel? Dishti Saha? Ritik Roshan? Jyoti Kumari? Mamta Kumari? Navneet Kumar? Okay, so who has got the answer? Who can you write your answer in the chat box? You calculate the this double second derivative using this central difference approximation scheme for at x is equal to 2 using two different step size, s is equal to 0.25 and h is equal to 0.125. Ayush, did you make calculations?
Yes, sir, in the final stages.
Okay, so you write the answer in the chat box. Only Ayush is active in the class, and Abhijit also, and Ankit Sarkar is not paying attention. Similarly,
Sir,
many.
we are also active, but we are not getting
Okay,
answers.
okay, Ankit, you are here. Very good. That's good. So you give the answer. So Priyanshu, can you calculate it? or any other step we need to discuss? Okay. So Ashish Kumar,
Yes, sir. Going on.
आंसर बताओ.
Yes, sir. कर रहे हैं, sir.
ठीक है, जल्दी सॉल्व करो थोड़ा. Ian is not at all attentive.
Yes, sir, I'm there.
Okay, very good. So give the response. You didn't give any response throughout this beginning of this course.
No, sir, I was not able to do. Actually, I'm doing.
So you try it on your own.
Yes, sir.
Okay, Bablu Kumar Patel. Okay. So some new people are giving, means people are not new, but some responses from coming from the people who are not answering. That's very good. Shekhar has given the answer. That's very good. But only some of the known your friends are giving the answer, and rest I do not know why you are not responding. Who has always given. Okay, you people. Deepti Priya.
Yes,
Kumar, okay, you give the answer.
yes, it's solving.
Okay. Yes, yes, Kumar.
Yes, sir.
Okay. So you have the slides. You can go back to the formula in case you want to refer that and give the answer. Rishabh has given. Saurabh Kumar Gupta has given. Ayan has given. Okay. So Ayan, you tried for 0.125 also. Saurabh, you also tried for the 0.125. Yes. Then we will proceed towards our next topic of today's class, that is numerical integration. Okay. So, who can suggest me which will give more accurate answer? That is h is equal to 0.25 or h is equal to 0.125.
0.125.
0.125. Okay. So using h is equal to 0.125, we will get more accurate answer, and you can check this by calculating the error or percentage error with respect to the exact answer or true value. So you can easily solve it. You try it on your own. I'm moving towards our next topic. So these are some of the numerical. You please try it on your own. If you are not able to solve, then we will discuss it. But I am very much confident that you will easily solve it, all these three problems. Okay. So coming on to this our next topic, the way we perform the numerical differentiation. In a similar way, there are techniques, methods through which we can uh, uh, get the solution for this numerical integration. So first, our approach is this trapezoidal method. So you have a look, you can easily understand this. At x is equal to a, the value of function is f of a, and x is equal to b, the value of function is f of b. So what if I wish to know the value at any point x lying between a and b, that is f of x. So using this similar triangle approach, I can express this f of x, that is value of function at point x at which is lying between interval a and b, in terms of fa and fb, that is written here, that f of a plus f of b minus f of a upon b minus a into x minus a. So you can use the similar triangle approach and get the value of function at this point. Now we know that area under the curve, if I have assumed a differential element of width dx, so the area under the curve will give me this this exactly will give me the integral, and this is only for the small element dx. So we have made a pretty simpler assumption, that is, we have multiplied with height, which was expressed as f of a into f of b minus f of a upon b minus a into x minus a into dx. And since this is only for dx element, differential element, so but we need the area under the curve between the limits a and b, so we will integrate this function which is represented by equation number 19, and this gives the area under the curve or the value of integral. So if we solve this equation number 19 or simplify it by substituting the limits, we will get something expressed by equation number 20. So this is called as trapezoidal rule, and in more specific way, this is single step application of a trapezoidal rule. So coming on to our next slide, that is slide number 16. The geometrically, the trapezoidal rule is approximately equivalent to approximating area of a trapezoid under a straight line connecting f of a and f of b. So we can recall that formula of computing area of trapezoidal is width times, you can alternatively calculate the formula, which is width times of times the average height. So width is b minus a, average height f of a plus f of b divided by 2, that is an average height. So which can be expressed as equation number 21. So average height, you know that this is f of a plus f of b divided by 2. Now comes another part of this question. We all know that we can calculate the exact error. What is the exact error with respect to the true solution? But one term I have introduced here is additional term I have introduced here is approximate error. So approximate error, you can see here, this is you have to remember this formula. We are not going to derive the derivation for this equation number 22. So you can see here that this is for a trapezoidal rule, approximate error. Once again, I repeat, this is approximate error, which is minus 1 by 12 f bar double prime epsilon b minus a. So now let us understand what is this f bar double prime. So this is average value of second derivative, which can be computed as mean is equal to integral limit a to b f bar double prime epsilon into d epsilon upon b minus a. So we will remember this, that the notation f bar double prime represents the average value of any of second derivative. It may be also a fourth derivative. So this is given by the mean value. So this is again an approximate quantity. That's why we call it an approximate error, not an true error. So in slide number 18, I'll read out this, where epsilon lies somewhere in the interval between a to b. Equation 22 indicates that if the function is being integrated is linear, the trapezoidal rule will be exact because the second derivative of a straight line is 0. So trapezoidal rule will be exact for a linear function. However, if we try to find the integration using trapezoidal rule with for a higher order polynomial, say fifth order, then there will be an error involved in the computation of integral. So let us have a look on a one solved problem. Using trapezoidal rule, integrate the following function between limits 0 to 0.8. So if you do it, integrate this function between limits 0 to 8, the exact value is 1.640533. And if we use this trapezoidal formula, or this single application of this trapezoidal rule, the formula is integral I is equal to p minus a f of a plus f of b divided by 2, and which gives us the value of integral as 0.1728, which is not at all correct because the true value is 1.640533. So if we look carefully, the graph of this function, which is represented by figure number 5, so we can see that the formula which we used, that is a single application of trapezoidal rule, you can see that it only calculated using this a line parallel to x-axis, and which is approximately exactly means which is having a high value of error, and error is represented by the above shaded portion. And in terms of error, it is 89.5%. So the reason for this error is evident from graphical depiction in figure 5. Notice that area under the straight line neglects a significant portion of integral line above the line. So figure 5 graphical depiction of the use of single application of trapezoidal rule to approximate the integral of fx. Now one more term was introduced, that is approximate error. So now let us compute the double derivative of the function of previous function, that is this function fx. So the double derivative is minus 400 plus 4050x minus 10800 x square, and so on. So if you calculate the average of second derivative, which comes out to be a value of minus 60, and once you substitute into the formula of approximate error, you will get to know this value is 2.56. So this was a single application of the trapezoidal rule. Now let us move towards a more. Oh, okay. Anyone wish to ask something or have a query in this regard? Okay, so you have a look on this. How we use this computed the integral of this function using single application of this trapezoidal rule, which is not giving us the correct answer. Now we will move towards our this computation of trapezoidal rule using composite trapezoidal rule. Let us see how do we do this. So in the meantime, if you have query, you may ask. So which is of same order and magnitude as the true error. A discrepancy does exist, however, because of factor of an interval of this size. The average second derivative is not necessarily accurate approximation of f prime, f double prime epsilon. So you can see that there is a certain deviation from the error calculated using this this approach, that is coming out to be 2.56, and you simply subtract with the error. I'm not talking about the percentage error, I'm talking about the true error ET with respect to the true solution. So the values are approximately of same order, which is 1.467733. So therefore, since it is not exactly same, that is equal to ET, approximate EA is not equal to ET, so we name it as give a name as approximate, not a true. So next is composite trapezoidal rule. Composite trapezoidal rule is again one step ahead of this conventional trapezoidal rule. So how can we improve the solution? That is, how can we improve the value of integral and get more accurate answer when compared with the exact answer? So these are some of the steps. One way to improve the accuracy of trapezoidal rule is to divide the integration interval from a to b into number of segments and apply the method to each segment. So same function, you can divide this x-axis into number of intervals, and each width of each interval is, if n is the number of interval and b minus a is the width of the interval, so length of each interval is b minus a divided by n represents the number of interval, and you can see here that h represents the width of each interval. So area of individual section can be then added to yield the integral for entire interval. The resultant equation are called composite or multiple segment integration formula. So figure 6 shows the general format and nomenclature we will use to characterize composite integral. There are n plus 1 equally spaced base points. So it is pretty straightforward that you can see that we have n equally spaced points. Consequently, there are n segments of equal width. So we have n segment of equal width. So simple method is that we compute the integral of each interval, that is integral of each interval, and add all the integrals. That is, if I1 is the estimate for the interval x0 to x1, I2, IT, I4, and up to IN, we can add up all these values and get the value of integral using composite trapezoidal rule. So here you can see that the value of integral for the first part, that is an interval lying between x0 to x1, is nothing but h into f of x naught plus f of x1 divided by 2, and so on. Once you simplify this equation number 25, we get the value of equation number 26. So 26 is the main equation for the composite trapezoidal rule. Here you can see that the extreme points are simply value of function at the extreme points are simply added up. However, we will multiply a factor of 2 with all the internal points. Internal points, that is value of function at internal points, is multiplied by a factor of 2, and whole function whole value is multiplied by a factor h by 2. So h is nothing but this is b by a divided by n. So 26, equation number 26 may also be expressed in a more general form, that is by equation number 27, and the approximate error is given by b minus a cube upon 12 n square into f bar double prime, f bar double prime. Okay, so you please have a look on this composite trapezoidal rule before we proceed towards one of the solved example. You have a look on this.
सर ये EA का फॉर्मूला सर कैसे आता है?
अब ये डेरिवेशन नहीं है तुम्हारे कोर्स में, ठीक है, तुमको थोड़ा सर्च करो अपने आप इसका कैसे आएगा, ठीक है, हम लोग फिर बाद में डिस्कस करेंगे. फॉर टाइम बीइंग यू रिमेम्बर दिस फॉर्मूला.
ओके सर.
सर यहाँ पर जो
एक एक करके हम लोग डिस्कस करते हैं. हाँ आयुष बताओ.
सर यहाँ जो एफ प्राइम डबल बार है, तो जैसे पिछले बार उसको इंटीग्रेट करके सॉल्व किए थे, तो यहाँ पर एन जितना भी इंटरवल बना उसमें सब में इंटीग्रेट करके इसका मीन वैल्यू आएगा. फिर
धीरे बोलो. क्या बोला? एफ बाद डबल प्राइम. हाँ
यस सर. तो सर
हाँ.
पिछले बार एक इंटरवल था ना, तो हम लोग इंटीग्रेट करके निकाल लिए थे.
हाँ
तो यहाँ पर तभी एन इंटरवल्स हो गए, तो यहाँ पर एन बार. यस सर.
नहीं,
तो
वो तो एवरेज वैल्यू लिया है ना, बी माइनस ए ही इंटरवल में लेंगे उसको.
अच्छा सर.
हाँ, अभी सॉल्व एग्जाम्पल देखेंगे तो उसमें कैलकुलेट किया हुआ है ये भी. ठीक है, तो अभी वी आर नॉट प्रोसीडिंग टुवर्ड्स. हाँ प्लीज टेल.
सर यहाँ पे एन सर डिसाइड कैसे करते, मतलब कि जैसे कितने इंटरवल्स में बांटना है, तो वो कैसे पता करेंगे कितना एक्यूरेट?
Okay, so means this n value in your exam you will get the need to solve the iteration up to n is equal to 2, which you can means solve in 10 or this 15 minutes. But once those who are good in programming, so or know the programming, you may develop a computer code for this, and you may take the value of n up to 50 or n is equal to 100 depending upon the this computation time. The higher the value of n, more accurate will be your answer, but the computation time will be more. Okay, so for this for your purpose, in exams you will be only asked for n is equal to say 2 or maximum up to n is equal to 3. Okay, so now let us proceed towards the solve example. So I have taken this n is equal to 2. So look here that you can solve this example using your this hand calculation easily. If I put this n is equal to 100, you can solve it, but you have to write a computer program for this. Although you will get an exact answer once you substitute n is equal to 50, n is equal to 20. but it is not possible to solve using this n calculations. So use two-segment trapezoid rule to estimate the integral of 0.2 and this integral which is given by fx, this function. So again the interval is from 0 to 0.8, and you have to use two-segment trapezoidal rule. So h will be nothing but 0.4, that is b minus a divided by 2, which comes out to be 0.2 value. So you see that we have simply added the value of function at extreme points. However, we have multiplied with a factor of 2 for the value lying between the extreme point. So this comes out to be 0.0688, and the exact solution, if we compute this value, comes out to be the 34.9%. So this is the percentage error, and the approximate error is 0.64. So this is the approximate error. So here we can look that again there is a difference between true error and approximate error, and the average value of function we previously calculated was this minus 60. So the result of previous example along with 3 to 10 segment. So you just now asked this how to decide the value of n. You can see that by taking n is equal to 2, the percentage error was 34.9%. However, once we made n is equal to 10, number of segments were 10, the approximate error reduced to just 1.6. But you see that there is lot of computation time involved in this calculation. Obviously, it is very difficult to solve using your hand calculations. You have to write a computer program for this, and the computer will also take a good amount of time to solve this. So you can see here that the value when n is equal to 10 is 1.6150. So let us proceed towards another topic today that we are going to cover is Simpson 1/3 rule. So Simpson 1/3 rule. So it is a better rule for the integration, or it is a suggested rule for an integration where the polynomial is of second order. So it is suggested that if a polynomial is of second order, then we may apply this rule. So based on this assumption, we will expand equation number 22 only up to x this f of this x2, and get the value of integral as denoted by equation number 13. And you can see here that now we have replaced a and b, which were the extreme points of the interval with x0 and x2, and get a expression for this get an expression for this Simpson 1/3 rule, which is represented by equation number 31. Again, you see that this is the extreme values of function are simply added. However, the inner points are multiplied with a factor of 4, and h is the this width of the interval. So here you can see that h may also be written, equation 31 may also be expressed by equation number 32, and we have replaced the term a and b with this x0 and x2. So a similar way, we also have introduced one term, approximate error here, like we did in this trapezoidal rule, and we get the approximate error that is given by equation number 34. You see that f4 is nothing but this is a average fourth derivative. We can easily calculate it, and it can this expression given for the approximate error, which is given in terms of h, may also be expressed in terms of a and b, or x0 and x2, that is extreme points. So this is represented by equation number 34. Now this is called single application of trapezoidal rule, and using this approach we will again solve the same function, and let us see how much error do we get for the same function which we solved using Simpson 1/3 rule. So if we have a look on this, the solution for this integral of the function given to us. So here we will substitute n is equal to 2 and h is equal to 0.4, and compute the value at different points, that is f of 0, f of 0.4, and f of 0.8, and apply this Simpson 1/3 rule, and we will get the value of integral as 1.367467, and the error involved is 2.730. In terms of percentage error, this is 16.66. So we have made a comment about the error, which is approximately 5 times more accurate, because error is approximately 5 times less than single application of trapezoidal rule. If you calculate the percentage error or true error with respect to single application of trapezoidal rule, and through using this single application of Simpson 1/3 rule, Simpson 1/3 rule is observed to be 5 times more accurate, and again we can always calculate this approximate error, which comes out to be 0.2730, and you see here that -2400 is the average fourth derivative for the interval. Okay, so this is was Simpson 1/3 rule, single application of Simpson 1/3 rule. Like we derived the formula for the composite trapezoidal rule, in a similar way we can derive a formula for this composite 1/3 rule. So figure 7, you can see here that there was a function. I have divided this function, we have divided this function into number of intervals between this a and b. So let us see how to derive proceed for this value of integral. So since the function is divided into number of this small segments, so the value of integral of each segment when added with each other will give us the value of whole integral, and which is expressed by equation number 35. We can also write this expression, that is for composite 1/3 rule for each integral gives us the value represented by equation number 36, and which may be rearranged to give us equation number 37. You can see here once more that we have this value b minus a divided by a factor of 3 into n. Again, extreme values, that is value of function at x0 and value of function at xn, are simply added up. However, all the odd points, 1, 3, 5, 7, 9 odd points, are multiplied with a weight of 4, and all the even points are multiplied with a weight of 2, and this we call is as a composite Simpson 1/3 rule. So this is expression number 37, which is also written here. You can see and correlate this with this figure. You see that we have given a weight of 1 to f of a and multiplied with a factor of 4 with this first point, and I is represents the inner point. I and j represents the inner point. So we have multiplied with a factor of 4 with this odd point, that is I is equal to 1, and next inner point is multiplied with a factor of 2, and this is how we do it to compute the value of integral using composite Simpson 1/3 rule. So this is all we can easily understand that as illustrated in figure 7, the odd point represents the middle term of each application, hence carry a weight of 4. The even point are common to adjacent application and represent counted twice. In simpler way, odd points are multiplied with a factor of 4 and even points are multiplied with a factor of 2. And you can see here that like we did for all the previous examples or the cases, that is a single application of trapezoidal rule, single application composite trapezoidal rule. In a similar way, we can make calculation for approximate error using composite Simpson 1/3 rule, which is given by equation number 38. And this f bar 4 is the average fourth derivative of the interval. So let us solve the same example, but using composite Simpson 1/3 rule and taking n is equal to 0.4. Since n is equal to 0.4, b minus a divided by n gives such h is equal to 0.2, and we can calculate the value of function starting from f of 0 to f of 0.8, and we see this value of integral is 1.623467. The true error involved in this case is 0.017067, and when same expressed in terms of percentage error, it gives a value of 1.04%. Once we talk in terms of approximate error, again it can be easily calculated, which is 0.017067. You can see here that it is the true error which we were getting was 0.017067, and the exact value and the error computed using approximate error is also the same. So this suggests that by application of composite Simpson 1/3 rule for the previous example we took gives an exact value of integral. So based on this what we studied today, you please try these numericals, that is question number 8 and question number 9 and question number 10 on your own. You can easily compute the exact value of integral and cross verify your calculations by calculating the relative this percentage error with respect to the true value and check your answers. So with this today's class is over. If you have a query, please wait for 5 minutes, and if you do not have and you wish to leave, you may please leave the class.
Thank you, sir.
Thank you, sir.
थैंक यू सर।
सर
Hello. Anyone wish to discuss anything?
सर आप वो ग्राफ वाला बता रहे थे, तो सर उसमें फर्स्ट जो टर्म था उसको 1 से मल्टीप्लाई किए, और उसके बाद जो ऑड या इवन था उसको 4 को और मतलब इवन से और 2 को ऑड से, सर वैसे मल्टीप्लाई करते जाना है।
इंटरवल कोई फंक्शन का है, ठीक है, 0 से 10 है, ठीक है। तुमने एफ ऑफ 0 कैलकुलेट किया, जो अब जो इनर पॉइंट्स होंगे वहां से हम आई कैलकुलेट करेंगे, उसको बोलेंगे आई इज इक्वल टू 1, 1 है क्योंकि the since it is the value is 1 which is an odd value, so it will be multiplied with a factor of 4, and the second point from the extreme value, point from the extreme value, it will be I is equal to 2, or here we have used notation j, so j is equal to 2, so that is an even value, so we will multiply that even point with factor of 2. So in short, I will say that you practice it and you will get familiar with this formula. Only means to get means to know this formula and understand the formula in a better way, you have to at least solve 2 numerical problems on your own, and only you will get to know that how to apply this composite Simpson 1/3 rule. Okay, Abhijit.
Okay, sir. Yes, sir.
First you try it on your own. Okay.
Yes, sir.
You have the exact solution also. You first you try it on your own, that you will get that what is fourth, what do we multiply the factor of 4, and where we have to multiply the factor of 2. Anyone else? आयुष?
यस सर।
वो तुमने उसको स्लाइड शेयर किया है उसका, ये वो जो तुमने पूछा था उस टाइम पर?
यस सर।
ठीक है, उसमें जो है एक डिफरेंट एग्जांपल देके उसको मोर इसमें फैमिलियर और इजी टू अंडरस्टैंड उसमें दिखाया है। ठीक है,
ओके सर, देख लेंगे।
ठीक है, सो विद दिस आई विल एंड द क्लास हियर and we will continue from the further topics, further means topic under this unit. Okay.